Okay, I think we can start. Welcome everyone. So we have about half of the audience live and half of the audience is online. So today we are very happy to welcome Ilse De Looze from the University of Ghent. And she started her PhD in 2009 and she quickly became an expert in Herschel data. And she completed her PhD in 2012. Then she went on to do a postdoc in Ghent, and then a few postdocs in the UK. First, she was a year in Cambridge, 2 years in London, and then she came back to Ghent. She has an ERC starting grant called Dust Origin, as you can see. And so her specialty is interstellar dust, but then on a galactic scale and on a cosmic scale. And this is also the topic of today. So please, Ilse, you have the floor.
Yes, thank you very much. First of all, thank you very much for the invitation. It's a great pleasure to be here. So during my talk today, it's a very long title, The Competition Between Supernova Dust Formation, Interstellar Dust Growth and Dust Destruction. So it basically boils down to the question, what is the origin of cosmic dust? So I list here my collaborators, and then I also want to briefly introduce you to the Dust Origin team in Ghent. So we have a few people focusing on different topics. So we have here the grain growth experts. So this is a PhD student, joint PhD student, doing lab experiments in Cergy with Professor François Delieu. Then we have a few people doing chemical evolution modeling. Stefan is a PhD student. Marco just started back in April, and we're doing this in collaboration with Monica Relano. Then we have two supernova dust destruction experts who just started. Nina started in April and Florian started in June. So he arrived just earlier this week. And then we have a postdoc, Jeremy Chastanet. He's working on characterization of supernova and interstellar dust properties. And then from my time at UCL, I also have a joint PhD student who's working on star formation history modeling, which also comes in very handy for the topic that I'll discuss today. So all these people work on interstellar dust, and if you haven't worked on interstellar dust, you may wonder, why should we care? Interstellar dust accounts for about 1% of the total mass of the interstellar medium, so of the low density gas that we have in between stars, so why should we care? And indeed, just to demonstrate how low density it is, imagine that you take a pint, you would fill it here with atmospheric air at sea level, then it would contain about 5 times 10 to the 22 particles. Take that same pint into the interstellar medium of a galaxy, fill it with particles, it would only contain 500 particles. So it's incredibly low density. Of course, this is taking the average ISM density. There is some variation, but just to give you an idea. So why should we care about this 1% of the interstellar medium? Well, there are a couple of reasons. First of all, dust is obscuring most star formation and most emission of stars, so about 30 to 50% of all stellar light is being absorbed by dust. So if we want to learn something more, especially about young stars in star-forming regions, we actually need to correct for this dust extinction effect. Secondly, we know that dust grains are efficient coolants, so they can enhance star formation, they can enhance the process of a cloud collapsing to form new stars. Then thirdly, we also know that the grain surfaces actually provide a perfect host for two atomic hydrogen atoms to meet and to form molecular hydrogen, which is a fuel for future star formation. And then finally, we also know that radiation pressure may play a significant role, so radiation pressure on dust grains to drive outflows. And these feedback processes, of course, are very important in driving galaxy evolution. So if we want to understand each of these 4 aspects related to galaxy formation evolution, we actually need to understand the dust properties. And if we want to understand the dust properties, the first question we want to ask ourselves is, where does interstellar dust come from? And this is exactly the question that I'm posing here today. So as a short introduction, a summary of the dust sources and sinks. I'm quite sure I don't have to convince you that you have AGB stars producing dust. Then, since supernova 1987A, we actually know that supernova remnants are also another stellar source of dust production. Then we have a non-stellar source of dust production, which is a bit controversial. We'll come back to that later on. It's grain growth, so it assumes that in interstellar clouds you have metals in the gas phase which can actually accrete onto the surfaces of pre-existing grains and grow bigger grains like that. Then the important dust sinks, the destruction processes, are in the first place astration, where you simply have a cloud that collapses to form stars, but this cloud actually contains some dust already, so the dust is going to be incorporated into the new star that is forming. And then we have supernova shocks. So when a shock is propagating into the interstellar medium, it has very high velocities, it can be a few hundred, up to 1,000 kilometers per second, so it's actually going to destroy the dust that it encounters on its way. So this is a brief overview of the sources and sinks. So why do we want to study the origin of dust problem? Well, there is a severe problem when we look in the low redshift universe, high redshift universe, and we actually make a catalog of all the stars and supernova remnants that are present there. We actually have a problem. We find that stellar sources are insufficient to account for the dust masses that we observe in galaxies, so both in the low and high redshift universe. So this would imply that we need grain growth to account for 90% of all the dust mass that we observe in these galaxies. And one very important plot that is actually often used to indicate, yes, we indeed need grain growth to account for the dust mass is this observational diagram. So this is one from a paper by Frederick Galliano, but has been published in different forms. So it has the metallicity here, which is nothing else than a metal mass over gas mass ratio on the x-axis, and on the y-axis it has the dust to gas mass ratio. So if a galaxy would follow this linear relation, that would mean that when you increase your metallicity, the same amount of metals would be locked in the dust grains, and the same amount of metals would be present in the gas phase. So the fraction would remain the same when you're growing in metallicity. However, what you can clearly see is that a lot of nearby galaxies actually fall below that linear relation, and they actually have a much lower dust to gas ratio at a given metallicity. So this actually indicates that either dust formation is not very efficient at these low metallicities, or there must be a very efficient dust destruction mechanism here. And typically the way people interpret this diagram is that because grain growth, of course, will be dependent on the metallicity, the amount of metals that you have available in the gas phase for accretion on the surfaces of dust grains, it is interpreted in this way that at low metallicity, grain growth is not efficient, and then you reach a certain critical metallicity threshold where grain growth starts being efficient and you start growing your dust mass in galaxies. So that's the reason or the interpretation of this diagram. But I'm a bit skeptical of just that interpretation, so I ask myself the question, does grain growth actually provide the only explanation for this observed trend? And then to give you an idea of the complexity that goes into this, typically people, so this is another version of the same diagram published in a paper by Peter de Vis, and he tried to explain the observations, so the different symbols all correspond to different observations of different samples. So he tried explaining these trends with different models. And as you can see, actually his models 4, 5, and 6, indicated with these colors, all give a decent fit to the observations. I'm sure you would agree. But then if you zoom in and you look at the model parameters for these specific models, so specific focus on the reduced supernova dust yield, so you have a standard dust yield, and then for supernova, so how much dust each supernova produces, and he in these models has decreased that number by these factors, and then you have the grain growth efficiency. So all these models actually give a decently good fit, but as you can see, the numbers are completely different. In both cases, there is less supernova dust production, but it goes from a little bit less to very extreme numbers, and the same goes for grain growth. I mean, there's a factor of at least 10 difference there. So there's clearly model degeneracies that play a role as well. So during my talk today, I want to discuss and highlight a few of the caveats that go into these kind of models and into the interpretation, and discuss a bit of the work that we've done to cover each of these topics, or we will cover in the next couple of years. So let me first start with the uncertain supernova dust yields. So it's since supernova 1987A that we actually came to realize that supernova and supernova remnants can actually also produce quite a lot of dust. Now there are various methods that we can study dust production in supernova remnants, and one is through modeling optical line profiles. So a very simple sketch. What happens is this is the expanding ejecta. In this case, it's emitting oxygen 3 emission for Cassiopeia A. So you'll have a blue shifted component that is moving towards you. You'll have a red shifted component. And imagine that you have dust formation in the central regions. What will happen is that the blue shifted component will not be affected by dust extinction, but the red shifted component will be affected. And that's actually clearly what you can see. So assuming this is, so in blue you see the observations, red is the model, and in yellow you have the dust-free model. So you actually have the dust extinction on the red side of the spectrum. So by modeling that, you can actually get an idea of how much dust is forming in supernova remnants. And while I was at UCL, this modeling technique was developed by Antonia Bevan, and we were trying to get more data from an observational site. We had a large VLT program to do that, and this is partly a result of that. So you can see we don't only have data for supernova 1987A, but we have data for a large sample of recent supernova and somewhat older ones. So if you just focus on the blue points, you can clearly tell that dust mass is growing in supernova 1987A, but what we can now say is that actually a lot of other supernovae seem to follow the same trend. So gradually over time, and this goes up to 30 years or so, we see a gradual buildup of dust mass in supernova remnants. The interesting side note to mention here is that actually models currently predict that all the dust should have formed in supernova remnants only, let's say, a few thousand days, so between 1,000 and 2,000 days. While here, clearly from the observations, we see that it's a much more gradual process. So that's, again, another inconsistency between model and observations, but something I won't focus on during this talk. Yes, okay. So let's move on to the second method. We can also study dust masses from infrared emission, and that's exactly what I've been doing with Herschel. Herschel has really been instrumental in doing this. So I'll show you a few results of two very iconic galactic supernova remnants. So the first one is Cassiopeia A. So it comes from a quite massive progenitor star. And you can clearly tell, so this is actually the prototype whenever people study the reverse shock and the forward shock. So first of all, you have the forward shock, which is just a blast wave which is moving outwards. But then when you sweep up enough mass, you also get a reverse shock that is propagating inwards. And you can actually see here the reverse shock that is heating the gas and the dust that you can find here on this location of the reverse shock. So looking at all the Herschel maps here, you can clearly tell when you look at shorter wavelengths that you're dominated by this hot dust emission in the reverse shock region. You still see it at 70 and 100 micron, and then it becomes a lot less clear when you move to the longer wavelength spire wave bands. And the problem is that at those wavelengths, the supernova dust starts to be at the same temperature or around the same temperature as the surrounding interstellar medium, so the dust that you have in the ISM. So you really want to disentangle these two components, and that's exactly what we've been doing in a project, in a paper for 2017. So maybe to show you what we did here is Scd modeling. So we first subtracted ISM emission, we accounted for some synchrotron emission, and then we modeled the remaining emission, as you can see here, the supernova dust emission. So actually in red here is the ISM dust emission, and then we have three different components in our spectral energy distribution model for three different supernova dust temperatures. So to give you an idea, focus on the blue part, we're interested in supernova dust emission, and we have all this contamination of other emission processes, from interstellar dust, from synchrotron emission, and a little bit of line emission. So we want to correct for that. And that isn't an easy job, because especially at these longer wavelengths where you're more sensitive to the very massive, to the cold but more massive dust component, you only have a small contribution from supernova dust emission. So eventually what we did is we did this kind of spectral energy distribution modeling for each pixel, and we could derive a supernova dust mass map. So actually what you can see here is on resolved scales where we think that more dust has formed in this supernova remnant. The first thing what you can notice, so I've indicated the forward shock and the reverse shock, is that most of the dust mass is actually present within the reverse shock region, and that's actually what we also expect, because if the reverse shock has been propagating inwards, if we assume that dust had also formed here in the past, but that it has been destroyed now by the reverse shock, then this is exactly what we expect, and then we could calculate destruction efficiency of around 70% for Cassiopeia A. This is, of course, this is not the best way to actually calculate destruction efficiencies from reverse shock processing, but it does give us some rough idea. And in the end, we get a total dust mass of around 0.3, 0.6. So to give you an idea, if for instance, because I focus now mostly at the low redshift universe, but in the high redshift universe, if we want to account for supernova dust to produce most of the dust that we observe in these galaxies, we need each supernova to produce between 0.1 and 1 solar masses of dust. So with this number, we're actually very close to the number for supernova 1987A, and it's a quite high number. Then it's very interesting to also look at the independent conformations for Cas-A. So around the same time, we actually got another paper on Cas-A, where Antonia Bevan, with the optical line profiles, also got a dust mass of around 1 solar masses. So again, independent evidence, and actually the first supernova remnant after supernova 1987A, where we could demonstrate that a large dust mass is produced. So that supernova 1987A is probably not just a unique case, but that there are other ones as well. And this is another study by Maria Nicolescu-Duvas. So what she has done, she's actually also looked at line profiles, but now comparing the oxygen 3 line profiles in the optical and in the mid-infrared. What you can see is that the one in the optical hasn't been affected by dust extinction, while the red one in the optical has been. So then if you make the comparison between the 52 micron profile and the optical profile, you can also get an estimate of how much dust mass there is in specific locations. So these observations were done with ISO, and you can see the ISO beams here. And if you look carefully, I don't know if you can read it, but it also has the numbers of the dust mass that you expect to be present. And the image in the background is actually the supernova dust mass map that we inferred from Herschel. And you can clearly tell the peak here is around, you have dust mass of 0.31, 0.23 here, and all the dust masses here are lower. So actually, from a completely independent method, we get a similar result in terms of dust mass, but also in terms of spatially resolved dust distribution in the supernova remnant, which is great. Then focusing on another iconic galactic supernova remnant is the Crab Nebula. It's a completely different object. It's a pulsar wind nebula. It has a rotating neutron star in the center, which is ionizing the gas. There are magnetic fields, so you're actually dominated by synchrotron emission, not only at radio wavelengths, but also in a lot of, or at a lot of the other wave bands. So if we then, let me quickly jump to this figure, if we make a similar figure, which is done based on our spectral energy distribution modeling, we can clearly tell, again, in blue, the same color coding, supernova dust emission somewhat peaks or dominates in the Pax wave bands, but now if you go to longer wavelengths, you get contamination, this time not by interstellar dust emission, by synchrotron emission. And you can actually also tell by just looking at the Herschel data. So the Pax data are clearly dominated by the supernova remnant itself, but if you move to longer wavelengths, for instance, focus here on 500 micron, then it really resembles a lot the emission that you observe at radio wavelengths. So we again had to really do a very careful job in trying to separate those different components, and we could make, again, a supernova dust mass map for the Crab Nebula. So what you can tell here, if you compare to the optical, so they're not on the same scale, but you can tell that, so for instance, these optical filaments where most of the dense gas is located are also actually the filaments that we see most of the dust mass in. So it seems that those are the sites of dust formation in the Crab Nebula. And we get a somewhat lower dust mass, so we get 0.03 up to 0.05, which is somewhat lower, especially compared to earlier predictions. But also, I should mention that the Crab Nebula actually originates from a somewhat lower mass progenitor between 8 and 12 solar masses. And actually, the conclusion that holds for both is that they both have so both Cassiopeia A and the Crab Nebula have a dust condensation efficiency of about 10%. So the amount of metals locked up in dust grains is around 10%, which is consistent with models as well. Now, you've seen, okay, the dust masses that we infer are still uncertain by a factor of 2, or even more, depending on the methodology that you use. And a big uncertainty is that we actually don't know whether carbonaceous grains, silicate type of grains mostly form. So we don't know what to expect. And that's why we have this method B+, I call it, where we don't only look at supernova dust emission, but we actually also want to look at the polarization aspect. So where you have a magnetic field and you expect grains not to be perfectly spherical, but to be more ellipsoidal or spheroidal, and then they will align with the magnetic field, so they'll get a specific orientation, they will all align, and then you expect dust emission to be polarized as well. So that's what we've tried observing both in Cassiopeia and the Crab Nebula. And I'll show the results here for the Crab Nebula. So we've used SOFIA HAWK Plus. Fortunately, we won't be able to use SOFIA in the future anymore because it will not longer be observing anymore. So it's great to still get these final results from SOFIA. As you can see, it's still it's a big struggle to still get a high enough signal to noise. So you see here the observations at around 90 and 150 micron, both of the Crab Nebula, but the pixels that are shown in color are the only ones that are detected at enough signal to noise. And this is just looking at the total intensity map. I'm also showing here the different apertures, the different ellipses where, so that corresponds to these filaments actually, where, so in the optical, where we also observe most of the dust mass. So we're actually observing at these wavelengths the peak of supernova dust emission, where we're really dominated by supernova dust emission. So then having a look at the results. So these are the maps at native resolution, where you can see so the different polarization vectors here. So they show the orientation of the magnetic field, and the size corresponds to the polarization fraction. So the larger the vector, the larger the polarization fraction. Of course, because the signal to noise wasn't that well, and because we want to compare to Herschel data, what we did is we smoothed the data. So you can see the resolution is degraded. And then we also had to correct for synchrotron, of course, because remember, there's always the synchrotron in the Crab Nebula, so we have to correct for synchrotron polarization as well. So that's what we did in a careful way. And then we focused our study actually on the polarization fractions within those 3 regions. So the 3 regions where we also have the highest supernova dust masses, in the hope to get a better constraint on how many carbon grains, how many silicate type of grains do we expect to be present. There are a few assumptions. It always jumps ahead. There are a few assumptions that have gone into this calculation. So we have assumed that carbonaceous grains don't align, so that only silicate type of grains align. So that's an assumption often made because there's a specific carbon feature at 3.4 micron, which doesn't show any evidence for polarization. So that's why people typically assume that carbon grains don't align. Then we've made the assumption that only large grains align, so up to 0.1 micron, so anything smaller than that doesn't align. So the confirmation that we already get supernova detection of polarized emission in the Crab Nebula is actually only the second one after Cassiopeia A. So this indicates that we have large grains. And why should we care that grains are large? Well, the grain size very much will determine whether or not, when we get a reverse shock like we've seen in Cassiopeia A, whether or not a grain will be able to survive. And somewhat larger grains will be more resilient to dust destruction in that way. So that's why we're actually happy that large grains are present, because that means the net supernova dust contribution can be somewhat higher. Overall, the dust polarization fractions that we get of around 10% are quite low, because in Cassiopeia A, 30% polarization fraction has been detected, but I should mention that that result is somewhat controversial still. And then we tried deriving a carbon mass fraction, but we only get a constraint that the carbon mass fraction, so the mass of carbon dust grains over the total mass of dust grains, is between 12 and 70%. So there's still a huge uncertainty. The only thing we can conclude is that both coexist. And part of the uncertainty here is because the models that you use heavily depend on the orientation of the magnetic field lines with respect to the line of sight. So you have to make a lot of assumptions, and we're not able to do that. So we have to allow for a lot of freedom in our models, and that's why you end up with something like that. So in the end, if we want to learn something more, we now had observations in 2 wave bands. You probably want to have even more wave bands. Okay, so let's now focus. So I think I convinced you that supernova dust yields are still somewhat uncertain, but that there are, after supernova 1987A, more cases where we actually now can really confidently state that supernova dust or supernova remnants produce dust. So let's focus now on grain growth. So the problem there is that currently people assume it to account for 90% of all the dust, but actually we don't know whether grain growth can take place. We haven't found any chemical formation routes. For instance, we know in the dense ISM, the problem is that once you reach a certain depth, you'll get the formation of ice mantles, and everything that accretes onto these ice mantles will be photodesorbed after cloud dispersal, so after the first stellar feedback processes or supernova going off, and then you'll have UV radiation, and so everything will be lost that has grown in that period of time in dense clouds. Then there have been some claims that you can get dust formation in diffuse ISM clouds. With diffuse, I mean then densities of around 30 centimeter cubed, more or less, so not very dense regions, more diffuse regions. And there are papers that claim that you can grow silicate grains in this way, but what they did have to change is that they had to kind of extend their grain size distribution to very small grains, because if you have smaller grains, they will contribute a larger surface over volume ratio, so you have more surface, and that's what you want, because the larger the surface is, the more efficient the accretion will be. And then they account for Coulomb attraction, because these small grains will be negatively charged, and then you have the positive ions in the diffuse ISM. Now, so this was actually great news back in 2016, 2018, but we've actually shown that a number of assumptions that have gone into this don't really work out. So just to give you an idea, so this is the density as a function of the silicon over hydrogen abundance in the gas phase that you observe. So you expect indeed, when you go to denser clouds, that the silicon abundance will go down, because it will be locked up in dust grains. So this is what they want to be able to explain with grain growth. And what they actually did is, so as you can see here, they extended their grain size distribution to somewhat smaller grains, but they actually never accounted for an evolving size distribution. They just assumed that their size distribution is going to stay constant, but of course, if you're growing your smaller grains bigger, it's actually continuously going to shift, and you need to be able to replenish your small grains. And that wasn't considered. And as soon as you start considering that, so this is actually the normal size distribution that we all typically use, the MRN distribution. This is where you go to somewhat smaller grains, then indeed you can actually reproduce. As you can see, you can reproduce it, but it's actually unphysical. So with the regular size distribution and the evolving size distribution, you can see we can simply not explain those 2 data points. When you go to very small grains, you can explain it, but then here we look at a galactic dust extinction curve, and you can see here the typical shape in red also that it takes. But then if you go to very small grains, you can see that you get too much dust extinction here at a shorter wavelength, so it's completely inconsistent with what we observe. So the assumptions that they made won't work in the diffuse ISM. So again, we're back to where we were before. We don't have any way of growing grains yet in the interstellar medium. So now let's focus on dust destruction. So typical dust lifetimes are of the order of 100 million years, 200 million years, but there is actually some evidence that this has been overestimated. So a first problem is that typically what people have assumed to calculate these dust destruction efficiencies is that you have a homogeneous ISM structure. So typically 1D models where you cannot account for the 3D ISM structure. But if you do, so there's some claims that if you do account for the 3D ISM structure, you'll have a clumpy structure where some of the dust will be hidden and locked up in denser clumps, and then you'll have a more diffuse distribution around that. And indeed, there are now some first simulations that hasn't been published yet, but that show that actually what happens when a supernova explodes is that the energy will actually escape through the low density channels, and a lot of the dust will remain unaffected. So dust destruction efficiencies have actually been overestimated somewhat in the past. And actually also from observational point of view, this is something in that was shown in a paper by Felix Priestley. So this is actually the MIPS 24 micron image that you can observe for a galactic supernova remnant. You can clearly tell here this is not a reverse shock, but this is the forward shock that is actually hitting the interstellar dust. If you take the spectral energy distribution within this annulus, so these are the observed data points, and you have a lot of information for the supernova remnant. So you have X-ray data, so you can actually calculate, okay, what are my X-ray properties, what is gas density of the gas, and what do I expect from collisionally heated dust, what would be my dust temperature. Then this would be the dust temperature that you expect, but you can clearly tell that there's the residual at longer wavelengths, so that shows that there's actually evidence for a colder dust component which doesn't seem affected by the supernova shock front that may be able to survive. So both from simulations and from observations, there is evidence now that we're likely overestimating the dust destruction efficiency in our models. Then finally, it may be that there's a variation with metallicity, and in a very simple model, this is something that in collaboration with Felix Priestley, he has done. So what he has shown is actually when you have a very simple model and you account for thermal sputtering, kinetic sputtering, basically elements in the gas phase or particles that are gonna collide with your grains and are gonna destroy it if your temperature is very high. So what happens if you go to low metallicity? Metals provide an important coolant of the interstellar medium and of gas in general, but if you have fewer metals present, that means that the gas will remain hot, so you'll get a lot of collisions still, and sputtering processes will remain active for longer. So you're actually, the duration during which you're destroying dust grains is going to be longer. And this is actually with some very simple models, something that he has demonstrated. It's not quantitative very much, so it's not something that can be used in models yet, but it does show that there is some variation and that we expect dust destruction to be more efficient at low metallicity. And remember, this diagram, which has been used up to now to actually account for grain growth, maybe that could just provide an alternative explanation. So it could be that dust destruction is just more efficient, that you still produce enough dust at low metallicities, but that dust destruction is more efficient, which would lower your dust to gas ratio. Then finally, there's the question on galaxy dust masses, whether they're overestimated, and that could be the case as well. So if that's the case, then actually we need less dust to form through grain growth to account for the dust masses that we observe in galaxies. And in recent years, it's actually been shown that indeed we may actually be underestimating the emissivity of dust grains. So to give you an idea, on the left-hand side in red, so these are all different dust models for the same dust mass. So if they would be equally emissive, you would expect the Scd to be the same, but this is the Drain and Lee model that's people typically use, and these are some more recent models, and they are more emissive. So if you would fit your observations with these more emissive models, you would actually get a dust mass that is lower by a factor of 2 or so of the order. And even maybe those new dust models actually are not emissive enough yet, because there are some laboratory studies here in a paper by Katrien de Meijk. She had 2 in 2017. So studying different interstellar dust analogs, and these are the typical astrosilicates used in Drain and Lee model, and the Themis model is this Jones model. And you can see here their mass absorption coefficients, and these are the ones that are inferred for all the interstellar dust analogs that were studied in laboratory. So a lot more emissive. So if that's the case, we may be severely overestimating the dust mass that we observe in nearby galaxies and possibly also in the high redshift universe. Also, another assumption that often is made, and a problem, is that we have a lot of constraints on Milky Way dust because we're in the Milky Way, but often people then are going to extrapolate and say, okay, we assume Milky Way dust to be the same everywhere and the dust to be the same everywhere. But that's, of course, not the case as well, and that's something that we're showing in a paper that is in preparation right now. So what we're doing is we are having observations for more than 400 galaxies. We're modeling those data with a typical Milky Way dust model for the diffuse ISM, and we're looking for deviations from those models. So in this case, what we get, and we focus at the longer wavelengths because there you're going to be more sensitive to the dust mass, and it's also been shown in laboratory studies that you may get a different effect at longer wavelengths. So what you see here, for instance, is that the observed blue data point is higher than the model. So in model are the red data points, but here they nicely overlap, so you don't really see them. So you clearly can tell that here there's a positive, what we call submillimeter excess. While here, on the other hand, the observed data point in blue is actually below the model extrapolation. So we call it a negative submillimeter excess or even a deficit. Now, if we do this for a huge number of galaxies, we actually find very interesting trends, which suggests that there's actually a variation in the submillimeter excess or the emissivity of dust grains when galaxies evolve. And in this plot in particular, so we show the excess here. So all these galaxies here have excess emission. All these galaxies show a deficit. And this is as a function of H1 over stellar mass ratio. So often this ratio is actually used to constrain the stage of evolution of a galaxy. So a galaxy would start up here with a very high H1 gas mass. Little has been converted into stars, so it's still a low stellar mass overall. And then a galaxy would gradually move in this direction, where more and more of the H1 gas is being consumed and more stars are being formed. So if we follow that evolution, that means that galaxies first would have an excess, so would have more emissive dust, and then gradually move on to have less emissive dust. And that's actually also what we see. So this is the same plot, but now not only with respect to this ratio of H1 over stellar mass, but we also looked at other quantities, like, for instance, the metallicity. So here we see at low metallicity, so again, a galaxy that is quite young, less evolved, shows more emissive dust. And the other trends more or less demonstrate the same thing. So it shows that there's actually, in galaxies, an evolutionary trend in dust properties. And if we don't consider that, of course, we'll get, again, dust masses wrong. So this last aspect I already highlighted before, so the simple by eye fitting. Yeah, I've already shown that you get hugely different parameters, so we cannot simply do by eye fitting. There are too many different combinations of models that are possible, so what we want to do is actually do a more rigorous study of the entire parameter space, and that's something that we attempted in 2020. So this is the sample that we have studied, so you see their distribution in stellar mass, H1 mass, specific star formation rates, and metallicity, to showcase that we're not covering a specific narrow range, but we're really covering a huge range of stellar mass, a wide range, stellar masses, and different galaxy types. So what we've tried doing, again, we look at this parameter that people in my community like to use to kind of indicate the stage of its evolution of a galaxy. So again, they start off here with a high H1 gas, low stellar mass, and they evolve in this direction. Then we look at 4 specific quantities. We look at their stellar mass, we look at their metallicity, at their dust to metal ratio, and their dust to stellar mass ratio. And then we try to reproduce the observations. So we've divided our galaxy sample in 6 different bins, so indicated by the different colors. And with our models, we're trying to reproduce, okay, with what kind of levels of supernova, dust production, dust destruction, grain growth, can I actually account for each of these observed data points, and for their amount of stellar mass, now their amount of dust mass in the galaxy. So that's what we've done, and we've considered 3 different models. The first 2 are quite simple, closed box models, and the third one accounts for gaseous outflows and infall of gas. And then the difference between the first 2 models, without going into too much details, are different star formation histories. Where in the first one we actually tried deriving a star formation history from observations, and the second one is a typical delayed star formation history model. So here what you can see, the same observational plots, so the gray points are all the data points for all the galaxies. The 6 different symbols show the different numbers that we get in different bins of galaxy evolutionary stages, and then the lines that you can see here correspond to different models. Now, the first thing that you can tell is that actually the model doesn't work very well at the low end and at the high end here, simply because here probably at low stages of evolution, so less evolved galaxies, it becomes very tricky because they're low mass and they're very fragile to gas outflowing, so it depends a lot on the prescription that you use. And at the high end, these galaxies have likely been recently quenched, and then it becomes very tricky as well. Maybe some gas has been removed. So we decided in the end, the bulk of the galaxies that we have here, more than 65–70%, is actually in those 2 galaxy bins here, which are well modeled. And we actually also know from galaxy evolution studies that in these galaxies, all the gas that is infalling is eventually used for star formation. So you actually have a nice equilibrium between the gas that is available and that is used up for star formation, which isn't the case on either sides. So we focused on those and then had a look at our results. So here you see a typical corner plots with the posterior probability distribution functions, so the 1D ones and then the 2D ones, where we look at 2 parameters at the same time and whether they correlate or not. So in these models, we had 4 different parameters. So the initial gas mass, which actually determines later on what metallicity you have, because you have a fixed star formation history. So your initial gas mass will be a lot sensitive to the observed metallicity. So actually, in all the models that we ran, it's quite well constrained, because it simply means you start off with some gas, especially in a closed box model, that will be used up to form new stars. And those new stars will pollute the interstellar medium, and in the end you have a certain metallicity, which is simple the metal mass over the gas mass. So that was always well constrained. And then the other 3 parameters relate, first of all, to the supernova dust yield. So we've used yields from the literature, where there hasn't been considered the fact that there can be a reverse shock, and that the eventual net yield that is injected into the interstellar medium will be lower. So this is actually a reduction factor to account for that. Then we have the grain growth efficiency and the dust destruction efficiency. So what we can learn from that is that actually we only reduce the supernova dust yields by a small factor, like 50% or so, not the numbers that I showed you before that people require to reproduce the observations. Our grain growth efficiencies are relatively low as well. Our dust lifetimes are somewhat longer, so we get somewhat longer dust lifetimes, 1 to 2 gig a year. I should mention that, in all honesty, there is still somewhat uncertainty in the models. So what you ideally want, like here, is that the posterior probability distribution completely goes down to 0. So it does indicate that we need better data to fully rule out some parts of parameter space. And also this actually clearly tells, so on this side you have the supernova dust destruction efficiency, so how much of the interstellar dust is it destroying, and then you have the grain growth efficiency. And you see clearly that there's a degeneracy between the 2. So you can actually keep on increasing both as long as they cancel each other out. And that's actually also somewhere understandable, because the prescriptions for grain growth consider how much molecular gas there is. Molecular gas is related to the star formation rate, and of course the number of supernova, and supernova dust destruction efficiency also scales with the number of supernova that go off. So you can actually keep on increasing both, and so there's a clear degeneracy there, and that's also what other studies actually have been hampered by, because you can just play with the parameters a little bit, and that's what we show with our study here. The main takeaway message is that we've actually found an alternative, and that we don't always need grain growth to account for all the dust that we observe in galaxies. This is definitely not the final end study that we'll do on this topic, because of course we've still made quite a few assumptions, but I'll get back to that later on when I talk about future work. So just to highlight, this is actually depending on the models that we have assumed. So you can see here the stardust, so how much the buildup of stardust over the lifetime of the galaxy, and the same for grain growth. So present day dust masses are dominated by stardust, and especially if we integrate over the galaxy lifetime, we actually find 90% of all dust that could come from star dust in these galaxies. Now, I should mention that after we did this study, similar efforts have been done in the literature as well. This is a study by Frederick Galliano, so the same guy who actually published this, and actually using a similar framework, but with somewhat different parameters. So again, this is a posterior probability distribution plot, and what you can tell here, so this is an interesting parameter to focus on, are the supernova dust yields. So this is 10 to the minus 2 solar masses per supernova, so you can tell that he actually finds a lot lower values. And one aspect of the study is that he actually goes down to very low metallicities than we do, so really considering the data points here, while probably our data stops somewhere around here. So he has this scale of low metallicity data points, and if you then assume that your supernova dust yield, so how much dust a supernova produces per supernova, remains constant across metallicity, then of course to explain these very low dust to gas mass ratios, when you do a hierarchical Bayesian model, you end up with very low supernova dust yields. So it depends a lot on what assumptions you put in your model as well, and you can get different results, like here is the case. But as I've shown before, actually these low supernova dust yields are completely inconsistent with what we observe in supernova and supernova remnants. Then another comparison to the literature, so I plugged those figures from those papers. So here you have, maybe focus on the right-hand side, the specific star formation rate over the specific dust mass, so the dust mass over stellar mass. So you have the data points here, and so maybe focus here on their solid lines. So without dust growth models, there's the orange curve here, which accounts for outflows. So here they're actually reproducing observations for low metallicity dwarf galaxies by accounting for very efficient outflows. But I should mention that in this study, actually, they didn't do a rigorous search of parameter space, and it was more, by eye fitting, let's say so. But I think this shows that there's not a general conclusion yet within the community, and that different people actually using somewhat different model assumptions get very different results. So takeaway message, I think the current picture of grain growth dominating 90% of all dust that we observe in galaxies is definitely too simple. By doing a rigorous search of parameter space, you can find different solutions for sure, and that it also works with efficient supernova dust formation, which is in line with the supernova dust masses that we observed in some galactic supernova remnants. But of course, as I've shown you as well, we need to fine-tune our chemical evolution models. We need to refine our models for grain growth, for dust destruction efficiencies, accounting for metallicity dependence, for the 3D structure that is present in the ISM and not just the homogeneous media. And we also need to refine our supernova dust formation models. Currently, statistics are still somewhat low. I haven't presented everything. I've just focused on two iconic galactic supernova remnants, so we do have more data But typically when we observe a large sample, for instance, we look at all galactic supernova remnants covered by Herschel, then we typically find detections in around 20%, 1/5. If you do the same exercise in small or large Magellanic Clouds, you get the same number. So the question is then, is only 20% producing dust? Most likely that's not the case, because there's always a bias that those 20% clearly have another heating mechanism. Either they're pulsar wind nebula, such as the Crab Nebula, or they have an ongoing interaction with the interstellar medium or circumstellar material, which is actually heating the dust to higher temperatures, so you can easily distinguish it from some interstellar dust, because the temperature is somewhat higher. But that's something that future work will need to tell. But the future is definitely bright. We'll soon get the first observations from James Webb. James Webb is gonna look at supernova 1987A, at Cassiopeia A, gonna be able to really resolve clumps of dust in Cassiopeia A, so get constraints on typical clump sizes, density contrast, so we can really refine our models to try to see, okay, what is now the dust destruction efficiency that we expect. We're doing some lab studies of grain growth, which I think is really the way forward to see really, okay, can we indeed grow grains in the interstellar medium? And we're not the only group doing that. And then there are some groups already working on this, and with the people who just started in our team, we're also gonna tackle this problem, so look at supernova dust destruction efficiency. How much does it go down when we indeed account for this 3D structure? And then we're gonna use all that information in our improved chemical evolution model. So we're already implementing some things, as you can see here. I'm not gonna bore you with all the details, but stay tuned for sure. Thank you very much.
Very interesting talk, thank you. Are there any questions? I will bring the micro to you then.
Ilse, when you talked about the dust emissivity, there was a plot with, in lower metallicity, you have a very efficient emissivity in the far infrared.
Yeah.
Is that that's related to the species of dust that you form there at low metallicity, or is that?
We don't know. We don't know. Yeah. So we've observed these trends, but it's unclear. So we're trying to see now: is it mantle properties? Is it carbonaceous versus silicate features? So that's some of the things that I've been trying to investigate for this paper, and I didn't find any explanation. So trying to see whether it's the ratio of carbon versus silicate grains, with carbon grains being somewhat more emissive. But it's also difficult because dust models are currently always being updated, and then silicate grains become more emissive. But we haven't been able to find any explanation so far what could be the cause. But it must be indeed that grain properties are different, but what exactly is going on is unclear at the moment.
Because I can imagine that it's on the silicates, but on the carbonaceous, then you probably don't need you don't need many refractory elements, I guess, for C.
No.
Carbon-rich dust. So,
no.
Yeah. Okay, thank you.
Yeah, it will be very interesting to study this in more detail.
Thanks for the nice talk. I had a question about the clump-like formation in the dust that is around supernova remnants, and what is the mechanism for the formation of such clumps? Is it dependent on the properties of the progenitor itself, like the rotation, the magnetic field?
So you mean, wait, let's see.
So for example, in Cassiopeia A, like, so yeah, the particular form, or in the crab, yeah.
So you mean the different clumps that we observe here in images like this?
Yeah, the structure and the, so that we see in the dust around the supernova remnants, are they dependent on the properties of the progenitors itself? Or
I think it's also, it depends a lot also on the explosion and explosion mechanism. So something that has been shown is that you don't yeah, you don't keep the typical onion structure, and that there is a level of mixing, and depending on the mixing, and also you can have asymmetric explosions, which is definitely the case also for Cassiopeia A. So depending on the level of the asymmetry and the level of mixing, I think that really will determine which elements will actually yeah, get in contact, let's say, and be able, so for nucleation to take place and to form specific grains. So first you'll have CO formation, silicon oxide, and then from that you'll grow carbonaceous grains and silicate type of grains.
Okay, thank you.
Yeah, so you had plots where the damped Lyman alpha system showed up at low metallicity but high dust content. Can you comment on that?
Yeah, here, yeah. The red ones,
Yes.
yeah. Sorry, I didn't get the question.
Just can you comment on what, I mean, what is the dust origin in there?
Yeah, so first of all, there is a little bit of uncertainty where they lie. So indeed, they seem to follow a constant dust to metal ratio, but I know the dust mass is not always that easy to derive in these objects. So there is some observational uncertainty. But I think, yeah, it's the same. I mean, these are also high redshift galaxies, and they have the same problem as well. But it's interesting indeed that once it would get confirmed that they lie along this line, this linear trend, it would indicate, because we expect galaxies that lie along this trend that they would be mostly produced by stellar dust. Because of course, stellar dust is, stars produce metals, some dust forms in stellar sources, as we've seen, so then you gradually grow up your metal content and your dust content. That is the idea. So then, following that interpretation, it could be mostly stellar dust, but I think it needs to be confirmed whether or not these galaxies lie on this trend. Because typically depletion levels are derived from zinc, assuming that zinc isn't depleted, and then, yeah, and we don't know whether that's specifically the case.
You mentioned the ratio hydrogen H1 over stellar mass ratio, and that is expected to decrease in time because the H1 is consumed in stars. Yeah. But on one slide you also mentioned H1 infall, because there may be that the H1 is also replenished, and maybe that can also influence there. And how much is that constrained? And could there be more H1 infalling on a typical galaxy than that there is consumed in stars, or is that observationally very clear and theoretically? So
yeah, one argument that observationally people have looked into is whether some of these galaxies, because it's low metallicity galaxies, and we know that they have very large H1 envelopes that don't participate in star formation whatsoever. And even if you account for that, you would still keep this trend, so that wouldn't play a role. So I think if that already doesn't play a role, then I don't think the infall of gas would play a huge role as well. And then in our study of the chemical evolution, it may play a role to some extent, because we had difficulties producing the observations at both ends. Let me quickly... Yeah, maybe here. So we had difficulties producing some of the more extreme ends of galaxy evolution, so the less evolved galaxies and the more evolved galaxies. So it definitely plays a role, but I think for these galaxies it doesn't, because for these ones they really seem to be in some equilibrium stage where, okay, you have some gas infall, it's being consumed right away, while for these galaxies indeed you may have an extended envelope where gas is not contributing, they're low mass systems, so you can get a very efficient outflow, and then it's not well accounted for by models because it depends on the timing of that outflow. It could have taken place a few million years ago, it could have taken place, 100 million years ago, so it's those systems are definitely very sensitive to these things, for sure.
Thank you.
You show quite convincingly that there are degeneracy between the growth and the supernovae or the production of material.
Yeah.
In the supernovae, is there any way to lift that? Because conceptually it seems logical that it's degenerate.
Yes, I think, so one aspect is that normally what's currently models for grain growth don't account for is the availability of metals. So they have simple prescriptions, and at least most models, there are some models already, but where you can simply keep on growing dust, but yeah, at some point you're gonna run out of metals. And the way we're trying to deal with this is we're implementing a key element approximation where you're gonna track down some specific elements like magnesium silicate, silicon, to really know, okay, I need these elements. If they're not present anymore, I'm not gonna grow silicate grains anymore. So that's the way around it, and at some point you won't get this anymore because you simply know, okay, grain growth stops here, it's not gonna be efficient anymore.
And then I had another question. There is another type of dust producer that you did not mention, that are the carbon-rich Wolf-Rayet stars that are in binary system.
Yeah.
Is there any constraint on the formation of grains and their growth that you can learn from those binary systems? Because they might be simpler than supernovae explosions, for example.
Yeah, that's true. Yeah, I think, yeah, that's definitely something else to consider. That's true. More, yeah, other sources as well. Yeah, I don't know out of the top of my head, and I think we'll learn more because there's a James Webb program as well targeting one specifically. So it will be very interesting to wait for the outcome of that.
Thank you. Any more questions?
It's not for the quantity. For the people online, Hans was asking whether there were enough of those systems compared to supernovae. I don't think necessarily this is for the quantity of those that they produce, but to understand the formation process.
Okay, if there are no more questions, then I would like to thank Ilse again. Thank you very much.
Thanks.
I think she's about half an hour that she can stay, but then she has to leave. So if you want to grab her and ask her something, so we have about half an hour.